Uncle Mike always said I could take anything apart, but I couldn't put it back together. And this didn't fit in very well with my mother's plans that I would become a surgeon. The point is, ever since I was little, I wanted to get to the bottom of things. My name is Steve Gottlieb. I'm a physics professor at Indiana University and a visitor here at NCSA. And I'm here for my sabbatical, and my field of research is high energy or elementary particle physics. What we're really trying to do is calculate the masses of bound states that are formed by the elementary entities in quantum chromodynamics. These elementary entities are known as quarks, which is a name that precedes the theory, and then gluons. So gluons are kind of a funny, amusing name. Particle physicists are known for making funny names for things. So the gluons make the quarks stick together. And so they form these bound states, and what we see in nature are really the bound states. We have something currently called the Standard Model of Elementary Particle Physics, and this model has 3 generations of quarks, and it has 3 generations of these particles we call leptons, like the electron, the muon, and the tau. And it describes most of the experiments we can do now in these high-energy laboratories. However, there are other observations that we can make, and is a very important missing particle, which is called the Higgs Boson, which the Large Hadron Collider has been constructed in order to see. Now, it's possible that the Large Hadron Collider will see many things more exotic than the Higgs boson. In fact, it would be kind of boring if all it sees is the Higgs boson, but you know, that could be what nature's like. Now, there are cosmological observations that have been going on for about the last decade or so that indicate the matter that we know and love, like protons and neutrons, only makes up about 4 or 5% of the mass of the universe, and that there's something called dark matter, which should make up about 20% of the mass of the universe. And in our current model of elementary particle physics, we don't have an elementary particle that would naturally be the candidate for the dark matter. So as much as we know about the world, which is quite a bit, there are still very compelling mysteries to investigate. On blue waters, the most straightforward thing that we can do is to take problems we're currently running and refine the grid size so we have a smaller spacing between the points in our grid. Blue waters, being a bigger computer, will allow us to go to a smaller grid size than we've ever used before and have better control of our errors and thus give us more accurate results. We are also exploring different formulations of the theory that require more flops than the older formulations of the theory, but reduce different types of systematic errors. So we're starting to do simulations that actually include the effects of a charm quark. Up till now, we've only been including the lightest 3 quarks in our calculations, up, down, and strange. And right now, we're just starting to explore putting in the charm quark as a dynamical quark. So that's an exciting thing. The larger collaboration I'm in, which is called the US QCD collaboration, applied for and received a PRAC award, which means that we should get early time on blue waters. And so there's a large group of people in our collaboration who have several codes that we need to port to blue waters. And I'm here, and it's really helpful because I can interact very directly with the people like Greg Bauer, who works on the simulator and has access to much more information than I do. And I have access to much more information than the other members of our PRAC team at this point. So I'm excited to be preparing for the arrival of blue waters and getting our codes ready. Certain things on blue waters are very new, like the VSX unit. So there's a new set of commands that you can give the computer or the chip that will run floating point computations very quickly. And the compiler may or may not really be able to effectively use those commands, whereas a human who knows exactly what we want to do may be able to cleverly put these commands together, because he has much more insight than a compiler can, and use the VSX commands in a more effective way. So that's a new feature of this chip. The feature of symmetric multi-threading is something that is available on other chips today, but Blue Waters will have a higher level of symmetric multi-threading than most of the chips we currently run on. And so we don't tend to use that very much, but we do have within the US QCD software library something called the QMT library, which is the quantum many-threaded library. My codes currently do not use that. The Chroma code uses that set of libraries, and it helps to speed the code up on some architectures. So one of the things to explore while I'm here is whether QMT is valuable for other parts of the code. The quest to understand the world around us it seems to me it's as old as humankind. And for me, it's just undeniable that I want to get to the bottom of things. And people have been asking the question of what is the world made out for 2,000 years or longer. And one time we thought it was earth, fire, and water. We've learned so much over the last few hundred years about how the world works that I think it's essential to continue this quest.
The University of Illinois' National Center for Supercomputing Applications provides powerful computers and expert support that help thousands of scientists and engineers across the country better understand our world. With the computing power available at NCSA, researchers create computer simulations with real-world social and business impact. NCSA is supported by the State of Illinois, the University of Illinois, the National Science Foundation, and other federal agencies.